Hello, everyone. Welcome to this session where we'll be discussing the techniques and methods for validations of inverter-based resource unit and plant simulation models across multiple simulation domains. My name is Parama Charoenphon, and I am an IEEE PS student currently study at Kasetsart University. At present, I am also participating an internship program at Hitachi Energy. In this video, we will delve into the critical aspect of validating simulation models for inverter-based resort in power systems. Here are the topics we'll be discussing in this session. First, we'll go through the introductions, and then we'll talk about types of components model for the validations IBR models, and then the key points for the model validations and the boundaries of the simulation domain capabilities and model itself. We are going to talk about, we are also going to talk about the appropriateness of a simulations domain. Note of you the short circuit ratio and the example of the model validations. And lastly, the ongoing efforts for improving the accuracy of models. Recent disturbance involving IBR have highlighted the need for accurate model validations. IBR, such as solar and wind farms, are increasingly integrated into the power grids, and their dynamic behavior can significantly impact the system's stabilities. To ensure reliable and safe operation, it's crucial to have models that accurately represent the real-world behavior of these resources. In the world of power system modeling, we use a variety of models with varying complexities. These models are used across different simulation domains, each serving a specific purpose. For example, steady-state powerful system model are used for analyzing reactive power and voltage, while electromagnetic transients are used for studying fast transients and unbalanced conditions. Harmonics are essential for evaluating voltage and current harmonics, distortion level, and identify resonance through impedance scan. Protection models play a crucial role in determining fault current with voltage control current source model of the IBR element gaining prominent for their accuracy in reflecting fault currents from inverters. Digital real-time simulations, also known as the RTS models, is a subset of the EMT models, enable real-time testing of closed-loop system control system protections and operating scenario. Small signal models, linearized around a steady operation point, are used to determine the small signal stability of the IBR unit and system. Hybrid domain models combine models from different time domains, offering a balance between details and computational efficiency. To be noted, it is important to choose the right model and simulation domain for specific study you are conducting. Protections model play a crucial role in determining fault current, with voltage control current source models of the IBR element gaining prominence for their accuracy in reflecting fault currents from inverters. Digital real-time simulations models, also known as DRTS, is a subset of the EMT models, enable real-time testing of the closed-loop control systems, protections, and operation scenario. Small signal model realized around a steady operations point are used to determine the small signal stability of the IBR unit and the systems. Hybrid domain models combine models from different time domains, offering a balance between details and computational efficiency. It's important to choose the right model and the simulation domain for the specific study you are conducting. When evaluating IVR model quality, a few main factors come to the forefront. First, reasonable parameterizations of the model that reflects its underlying characteristics. Second, expected response of the model to common voltage and frequency disturbance. Third, model response reflecting the trend of the response from representative equipment. And lastly, numerical robustness of the model. The model validation process provides direct comparison between the simulation domains and the actual product performance. Generally, real product performance should be validated against an identically parameterization EMT model of the IBR unit. In this comparison, both the IBR models and the product response are expected to match with a tight terrain after accounting for measurement accuracies and simulations software nuance. This process is also known as type testing. If the EMT model performance sufficiently tracks the trend of the HIL, it can be assumed that the EMT model is validate representation of the specific product. With this assumption, additional more tests can be performed that may have been too severe or complex to perform in an HIL setup. When performing model validation testing in a simulation space, it is very important that all parameters in our model under test can be verified to be identical to the product, that the underlying model codes utilize those parameters identically or with known mapping. In addition to the previous set, the following test as an example can be performed on both EMT and the PD models. With the power plant controller interfacing with the individual inverters. Best practice is to compare signals from the identical locations in all tests to evaluate any small discrepancy between the simulated test and the HIL test. This will highlight small difference in response due to simulation solution engine and allow manufacturer to provide explanations for applicable discrepancy between the model and the product performance. Component model validations across simulation domains. In example, EMT against PD should have a comparative wider terrain for match, with any discrepancy explained. A difference in solution engine can be produced slightly different yet still representative performance. This figure describes how model quality testing might fit into the process of designing, interconnecting, and commissioning a new IBR plant. Namely, one round of IBR unit or supplemental IBR device model quality testing, as previously described, might be done briefly by an OEM prior to embark on the detailed IBR plant design evaluation phase and with subsequent testing during the timeline of models. This step carried out by an OEM would be a comparison of the model behavior against type testing of hardware or the HRL setups. Further, once this validate IBR units model is obtained, it can be subject to an entire suite of model quality suite to that aim at ascertain the numerical robustness and precision of the model. The validate IBI unit models is subsequently used in the design evaluations phase of the entire plan. During this stage, if changes are made to the IBR unit model, then it can trigger another round of the IBR validation test. At the end of the design validation process, a verified power plant model is obtained. Here the term is used because at this stage, the performance of the IVR plant model can be compared against the performance requirement in the appropriate grid code or the standard. This verified model can subsequently run through the numerical robustness model quality test and be incorporated into the planning study. Once the plan is built, during commissioning, The IBR plan can be validated using measurement data. Subsequently, another round of the model quality test may be run before the use of the IBR model connect in the interconnection-based cases. The distinction between the applicability of a simulation domain and that of a component model within these simulation domains is important. The limitations of the IBR model that is available for a planner today do not necessarily reflect the capability of a simulation domain ability to capture various behavior. When asking for model, it should be kept in mind that the mere availability and use of detailed simulations will not automatically solve all issues presently being faced. Representing various behavior in a simulation domain depends upon the following. First, the use of the appropriate domain. Second, the accurate, appropriately parameterized and validate model of the IBR and supplemental device such as relay or the corrector network based on clear and explicit model requirement and accurate representations of the power system network, such as topology status, electrical characteristic, and load dynamic behavior. The ability to simulate the initiating event. The first 2 points help effectively highlight the nuance difference between the capability of a particular simulation domain and the IBR model in the simulation domain. One can use a very detailed simulation domain, but the study result can be inaccurate if inadequate models are used. The appropriateness of a simulation domain. EMT model is represent each phase of a three-phase system individually, capturing detailed interactions and imbalance. It varies according to varying frequency, making them suitable for study fast transients and high-frequency phenomena. Operate with a very small time step, allowing for precise modeling of repeat control action and protection mechanisms. It require more computational power due to their detailed representation and small time steps. Positive sequence phasor domain. It simplify the representation by focusing on the positive sequence quantity, assuming balanced conditions. Primarily valid for fundamental frequency phenomena and frequency up to approximately 10 Hz around the fundamental. Operate with a larger time step, making them computationally less intensive than EMT models. It is suitable for a larger scale simulation and study where detailed phase interactions are not critical. Choosing the appropriate simulation domain depends on the specific goals and requirements of the study. EMT models are preferred when detailed phase information, fast transients, or the high-frequency phenomena are important. PD models are suitable for larger scale studies, fundamental frequency analysis, and scenarios where computational efficiency is a priority. The short circuit ratio has long been a key metric in power system analysis, offering insight into system strength. SCR is the ratio between the IBR plant rating and the short circuit megawatt ampere. At the connection point, without the IBR, historically, SCR has helped assess the impact on the IBR on the grid. In weaker systems, indicated by lower SCR values, IBR controls often struggle with stability, especially during dynamic events. While EMT2 can accurately model converter performance under these conditions, PD2 may face limitations due to their frequency range. However, These limitations are strictly tied to the SCR metric. As IBR penetration grows, the traditional SCR concept based on the short circuit current from synchronous machines lo- lose relevance in the future. SCR might still indicate system strength for the basic IBR performance testing, but it shouldn't be solely relied upon to guarantee real-world plant performance. Model validation is a critical process to ensure the accuracy, reliability of simulations. Let's delve into some real-world examples from different perspectives. The first one is the IVR plan developer perspective. Developers focus on validating models by comparing their responses to frequency and voltage changes against field test data. For instance, they might assess how well a model predicts active power output in response to a frequency step change, or how accurately it simulates reactive power voltage control under varying voltage conditions. Utilities like Hawaiian Electric Company leverage real-world data from digital fault recorders to validate both PD and the EMT models. This approach helps identify discrepancy between model predictions and the actual system behavior during disturbance, highlighting areas for model improvement. However, challenges arise when validating models for the older inverter due to limited support for the manufacturers. System or perspectives such as Electricity Reliability Council of Texas utilize phasor measurement unit to validate models. By comparing model simulations with PMU data during the actual events, they can assess the model accuracy in predicting power response and identify potential parameter mismatches. Researchers focus on verifying the robustness and accuracy of model under challenging conditions, such as low short circuit ratios. They may also compare different types of model to understand their strengths and limitations in capturing specific phenomena. The pursuit of accurate IBR models is an ongoing effort, with industry standards and guidelines playing a crucial role. The Hawaiian Electric Company has established a facility technical model review process that outline minimal requirements for PDEMT unit and include performance tests under various conditions. Electricity Reliability Council of Texas has also taken significant steps by mandating the submission of varied IBR unit EMT models for new internet interconnections and requiring benchmarking of PD models against EMT models. The North American Electricity Reliability Corporation is a key advocate for accurate modeling practices. They provide guidelines, white papers, and an update dynamic modeling guidance document to promote best practices in model accuracy and selections. Similar efforts are underway in other regions, such as Australia, where Australian energy market operator has exhibited requirements through their dynamic model acceptance test guideline. IEEE Standard 2800 and 2022 mandates the use of validated IBR unit and supplementary IBR device models, emphasizing the importance of model validation in ensuring compliance. The upcoming IEEE Standard P2800.2 will further define the specific test and validation criteria. Research and development efforts continue to focus on developing numerically robust models, advanced validation methods, and techniques for identifying appropriate simulation domains for specific scenarios. These ongoing efforts are crucial for improving accuracy and reliability of IBR models. Ultimately, contributing to a more stable and resilient power grid. In conclusion, validating IBR models is crucial for reliability and stability of modern power systems. Selecting appropriate simulation domains and using accurate, well-parameterized models are key to capturing IBR behavior under various conditions. Despite challenges like model discrepancy, parameterization complexities, and the need for accurate real-world representations, ongoing effort from industry, regulators, and researchers are driving continuously improvement. By adopting rigorous validation processes, following involving industry standards, and investing in research and development, we can enhance the fidelity and reliability of the IBR models. This will help stakeholders make informed decisions, optimize IBR plan design and operation, and ensure seamless integration into the power grid. And that will be all for this session. Thank you for watching.